Okay, let's solve the problem Stone Game 6. And Alice and Bob, as usual, they take turns playing a game. And there are some stones arranged in a row, and each player values stones differently. So for example, the first stone has a value 1 for Alice and has a value 2 for Bob. And typically we assume that both players know the other values and other player values, and they play optimally. And the winner is the person with the most points after all the stones are chosen. And in case if Alice wins, meaning that its score is bigger than the Bob's, then we return 1. If Bob wins, we return -1, and if there's a tie, we return 0. Let's try to solve this problem with a greedy approach. Now imagine these stones. I'm going to draw 6 stones, and then I'm going to draw 6 stones here. This will just represent the stones for Alice, and this one will represent the stones for Bob. Now imagine that this stone, and this stone has been chosen by Alice, and we have the remaining stones, and they're chosen by Bob. Okay, let me make it red. Okay. Now, what I want you to understand is that we have, for this configuration, let's say the Alice score is A prime, or you can just say, let's say it's A, and for Bob, it's B. Now, let's just take a stone, let's say this one here, and swap it with another stone like J. Meaning that is there a stone that Alice can leave, so he chooses not to choose this stone, and he selects this stone that is a different stone that he didn't choose in his first solution, in his first strategy. So he chooses this stone, this red ones. Now let's say we just leave this stone and we'll choose this stone J. So we know the stone J is selected by Bob. Now what happens that Alice leaves, let's say that A is Alice values from the problem statement, so I mean this, and B will be the Bob values, and B. So remember this too. Now when Alice did not choose the I stone, that basically from the current sum, we have the value of this stone for Alice in his score. So we just subtract this AI, and he leaves this stone. Instead, he takes AJ. So he takes AJ. Now the Bob then leaves the BJ, and he takes BI. By this swap, what we want to do, we want to increase the score of Alice and ideally decrease the score of Bob. So Alice wants to increase his score, or any player, it doesn't really matter. So for this case, Alice wants to increase his score and ideally decrease the Bob score. So we can rearrange this term. So we can have A minus, so we're going to have AJ minus AI, and for Bob we're going to have B minus BJ minus BI. what we want, Alice's score only increases. Now notice here what happened. We end up with these two sort of equations when we swap the AI and AJ instead. So we exchange these two solutions. We let the Alice take J stone and we let Bob take the I stone. So in this case, this is what we have at the end. Now, for Alice's score to be increased, AI minus AJ has to be positive, right? Has to be positive. Or it could also be 0, but ideally we want positive, right? So in this case, it will increase. And for Bob, we want this BJ minus BI to be positive. In this case, Bob's value, when the Bob's score will decrease if this one in parentheses is positive. So BJ minus BI is positive. I hope you see where we're heading. So we have now we have these two inequalities. Now we can have AJ greater than A1, or let's just keep it this way for now, and BJ is greater than BI. Now if we add this inequalities, the both sides, we're going to have AJ plus BJ is greater than AI plus BI. That is the clue. That is the insight. So you can see the Alice score will increase if he leaves a stone I, in this case, you see, it leaves a stone I, for a stone where the Alice values and Bob's values is larger. So this is larger than AI plus BI. So the optimal thing, so we can keep doing this swaps for every such pair. If there is still a stone that has been taken by Bob, such that the let's say its index is K, AK plus a BK is greater than let's say the Alice takes some AL plus BL. If that is the case, if there is still a stone such that we have this, so we can swap these stones. Instead, Alice could take AK and Bob will take BL, just like we did here. So you see, the Alice score will increase when we take a stone J instead of I, if the sum AJ plus BJ, so remember that A and B represents these two arrays, Alice values and Bob values, if AJ plus BJ is greater than AI plus BI. So what hints us that at their turn, the player will strategically, optimally, will choose the stone with the largest value sum for Alice values plus Bob values. So let's see this from the example. For example, we have 1, 3, and 2, 1, right? So Alice values, let's call it 1, 3, and 2, 1. What we have, the sum of 1 and 2 is 3. Now sum of 1 and 3 is 4. Now you see, it's Alice's turn, and Alice will choose the largest sum, the stone with the largest sum. It's 4. So Alice will choose 3. And then there's only one option for Bob in this case. Bob will choose 2. Now at the end, Alice score, and we're sure that at the end, both players have optimal scores. The Alice has 3 and Bob has 2. Now that we have the scores, we can compare them. So idea was to get this insight by assuming that we have some configuration where Alice chooses some stones and Bob chooses another stones, and we let the A and B be the scores of Alice and Bob respectively for this configuration. And then we said that there could be a stone, let's say, that has been taken by Bob, that can be swapped with A, the stone that has been taken by Alice. So we did that here. We said, okay, Alice will leave the stone instead. So that's why we subtracted AI from his score and add AJ. And Bob will leave the stone BJ. That's why we subtracted BJ and add the BI. And after that, we reasoned that we want, by doing this, any player, in this case Alice, would like to increase his score. In this case, Alice, A plus Alice previous score plus AJ minus AI. The previous score only increases if AJ minus AI is positive. So we write this down here. And the Bob score, notice that there's a subtraction. The Bob score decreases by this swap if the other player basically. So you're the one who's doing this swap, who's doing this strategy. So it's Alice. Alice increases his score, and the Bob score will decrease if this one in parentheses is negative, is positive. So we have this here, so we rearrange a few terms and end up with this one. AJ plus BJ is greater than AI plus BI. So previously Alice take the I stone, and he takes the J stone. So you see, he only takes J stone if AJ plus BJ is greater than AI plus BI. So for this reason, at their turn, the player takes the stone with the largest value sum for both Alice and Bob. So we just say Alice values and Bob values. For all of them, we add them up, so the respective values, and we sort according to this. And then in the code, we're just going to sort in decreasing order, and then the player will start taking the stones by turns. So we're just going to sort them. We'll sort the stones by the decreasing values, just going this way, and then this is going to be taken by Alice and Bob, Alice and Bob, and Alice, and at the end we're just going to compare the scores, A and B, and then we report the answer. So let's actually see the code. I have here submission, got a wrong answer previously when I solved this. And here's the code. Okay, let's just look at here. We have Alice values, and here we have Alice values and Bob values, and I put them in a pair, and then here you go. And then we sort them according to our criteria, and then we have Alice to represent Alice score and Bob to represent Bob's score, and then they take, starting with Alice, the stones. So Alice will take all the stones in even indices, and Bob will take the odd indices. And at the end, we just check the conditions. So that is all. That is how you can solve this problem by this reasoning. So you assumed so sometimes there are people who will call this A prime or A asterisk, so to mean that these are optimal, and then they arrive at a contradiction. That's sort of a way of proving. That's also called exchange argument. It's one of the popular ways of proving greedy approaches. So we use that. So we said we have AI and AJ. What if we just swap this? Is it possible that we can increase AI and decrease BI? Because that is optimal. That's what we mean by optimal for this current. If you're the player doing the swap, you want to increase your score by doing this. And for by doing every such pairs, we will increase our score. So then we arrived at this insight here, that aj plus bj is greater than ai plus bj. So then we sort this by this one. So that's how you arrive at a contradiction. That basically, if we call this optimal, and if we call b optimal, and then we could have reached in contradiction saying that, oh no, this is not optimal, because we can just swap. We can let Alice take the stone j instead of I, and in this way the Alice score would increase. That's how you reach the optimal answer. So you might have conjectured this at first while looking at the problems. You can say, okay, there has to be some idea. Let's say greedy idea. I first actually tried aj minus ai, so sorry, bj is smaller than ai minus bi. I tried something like that. I said, if that is the case, so I'm going to sort according to this rule, and then I see that this is wrong, so you can just prove this. So you might have guessed this at first, and then you could prove this by a contradiction, just like we did here. We actually didn't conjecture that this is the case. We arrived at this. Or you could have said that, okay, I'm going to sort this by aj plus bj, so basically by the largest values to smallest values, value sums, and then you would prove that. So that's the exchange arguments. In greedy approaches, the greedy problems are beautiful because they require this kind of stuff. Like you like reason about what could happen in an optimal solution, and then you prove. And this kind of problem do not often require advanced data structures or some obscure algorithms. You better know if in problems that includes like arrays and stuff like this, game theory, maybe number theory, you need to know a little bit of mathematics, and then proving stuff like this, yeah, then it's easy to solve. I hope you enjoyed it, and I will try to find such problems and post their solutions as well, because these are interesting. And for other problems, it's not that easy to see this exchange argument here. There might be other stuff, like you might want to reason a little deeper. So I'll try to find such problem and then make a video about them. So see you in the next videos.